In this session, we will talk about simple and compound interest. We will briefly describe simple interest just for reference, since in practice most computations are performed with a compound interest. First, let's consider simple interest. The formula that we have for the simple interest is described in this equation. Let's consider the case where there is an account with $1,000 in the bank. The account pays 10% per year. At the beginning of the first period, we will have an initial balance of $1,000. The beginning of the first year is considered as time t equals 0. Remember, our t for time represents instants and not periods. Anyways, after 1 year, we will have $1,000 we originally have plus $100. These $100 are the interest generated and accrued at the end of the period. That means that a fraction of the interest is not available as a fraction of the period has happened. The interests are realizable or collectible only at the end of the period. Computing how much we will have at the end of the period will be what we have in the present, $1,000, multiplied times 1 plus the number of periods times the rate. In other words, $1,000 times 1 plus 1 times 10%. Remember, the formula originally was F equals P times 1 plus N times I, like that. How much money will we have after 3 years? Then we will have F equals 1,000 times 1 plus 3 times 10%. That is, of course, 1,000 times 1.30, and the future value would be $1,300. Of course, a smart person would think that they could do better if they could decide to make 1-year contract. This because at the end of each contract of simple interest, a new contract could be issued to gain interest on previous interest earned. The complete balance, that is the capital investment and the interest accrued, could be the capital at the beginning of the next period. Therefore, the gains to the interest compounds as the interest of the previous period generate more interest as they become part of the capital in the latest period. Let me explain. If we are smart and we notice this contract, I suppose to have a 3-year contract, what we could do is we could have 3 times 1-year contracts. And therefore the balance that we could have could look like this. The future value at t equals 1 for the first year would be 1,000 times 1 plus 1 times 0.1. This future value is now F of t equals 1 equals 1,100. Now, instead of keeping the simple interest contracts, we can reinvest in a new contract. In other words, we can reinvest this result by computing the future value that we will have at t equals 2. What we have at the beginning of t equals 2, which is 1,100 at the beginning of the second period. Now we compute the interest for 10% and initial balance of $1,100. And the interest now is 110 as opposed to only $100 of simple interest case. So the total amount we will have at the end of t equals 2 would be $1,210. And we can further again compute now how much we would have at t equals 3. And that amount is 1,210 times 1 plus 1 times 0.1. This final result equals t equals 3 will be $1,331. We can compare now 1,300 to $1,331. It is clear to see that we have an advantage in using compound interest rates over our computations. If we select properly the periods, we could get better results. So in general, anyone that is using simple interest can turn it into compound interest just by selecting properly the periods for the contract. That's why in practice, everybody uses compound interest. So this simple interest we will not use again other than to explain it in this moment. And for the most part, we will be using compound interest. So as we saw for compounding, the compound interest, all we need to do is we need to take into consideration one period and then take into consideration one period at a time. However, we also notice that we could probably, since this period, one period at a time, is repeated again and again, we can take advantage of this repetition by using exponents at the time of doing our computations. For instance, the formula that we have for compounded interest is f equals what we have today times 1 plus the interest rate now raised to the power of n. F equals p times 1 plus I to the n. So for that 3-year investment, we would have the future value equals $1,000 we originally had times 1 plus 0.1 to the 3. When we do the math associated to that, we would get 1,331. So this is the single most important equation that we will use during the course. Of course, we can obtain the equivalent notation for the present value if we would know the future value. As the present value is the future value times 1 plus the interest rate to the negative n, where n represents the number of periods associated in the model. P equals f times 1 plus I to the negative n. Let's present a side-to-side comparison of simple versus compound interest. In this table, we can see that although in early years of the computation, the compounds gets ahead of the results to a single interest by a small difference, in the long term, the difference is extremely significant. That is why in the short term, slight differences in rates may appear to make little contribution. The real significant divergence is noticed after several compounded periods. So in summary, in this video we cover simple interest and compound interest. For the remaining of the course, we will only consider compound interest rates.